Hello, everybody. Welcome to the Data at Your Desk workshop on Introduction to R. My name is Semi, and I'm presenting this with my co-host Eli.
Hi, my name's Elijah. I'll be doing the R coding demos and also making sure that the PowerPoint is going on through.
All right, and just so you know, if you're watching this on Zoom, there should be a link in your chat with a Google Drive with some of the files you're going to use if you'd like to follow along. All right, so let's go over some of the things we're going to talk about in this presentation. By the way, if you have a quick question during this presentation, you can feel free to drop it in the chat if you're watching this on Zoom, and one of us will try to reply for it. If it's something you would like a longer response on, then please save it to the end, and we'll have a Q&A section towards the end. And we'll also be doing live coding during this presentation if you'd like to follow along. So the topics we're going to go over are the differences between base R and RStudio, how to create a variable, aka an object, and creating new data sets, arithmetic functions, importing data sets, some different forms of data analysis like ANOVA and regressions, how to make graphs, and then again, at the end, we'll do a Q&A.
We also have a Google Drive. We already mentioned this, but if you would like to see the link and you've missed out on the chat, we do have a whole drive with
a few different data sets.
Yep, in the presentation.
Yes. All right. So what is R? Before we get into how to use R, we have to know what R is. So it is an open source programming language that is commonly used in statistical analysis. And you'll hear a lot of people use the term base R, and this can refer to both the language itself as well as the default console that the language is used in. And keep in mind the programming language base R does not have to be used within the base R console. It can be used within RStudio, which is what we'll be working today. R can be used alone, but a lot of people use it in integrated development environments like Notepad, RStudio, Jupyter, and all sorts of things. So we recommend people start out with RStudio. And to be completely honest, even if you're not starting out, we still recommend you use RStudio, and there's a few reasons for that. It's the most popular open source IDE. There's a lot of different online communities and resources to help you use it if you get into any trouble. It's very easy to find these online communities and tutorials online. It's a streamlined system, so it's easier to do administrative tasks, and it has an easier learning curve than base R.
We have a side-by-side comparison.
Yeah, that's base R versus RStudio. So here's base R again. It's one panel that you just do everything in. And here's RStudio, and this has 4 panels. So panel 3 is the bottom left, and this is basically what you get with base R. This is the same panel that you see in base R, and it's where you do most of your work and write out your code. Panel 4 is in the bottom right, and this is where you can find files and packages or view graphs. Right above that, panel 2 lets you keep track of objects and data sets, which we'll talk about later in this presentation. And then panel 1 in the top left is where you can run scripts. So we'll go over all these things in this presentation, so don't worry about remembering everything I just said. We'll break it down in an easier way. So the first thing we're going to talk about is building objects. So it is one of the most important things to learn in R. It's basically a variable that R can read and understand. And it's a way of storing information, whether it's a single value, multiple values, or an entire data set. In fact, you can even store several objects into one object. And we'll talk about the different forms of data and the different types of objects you can make with them, but first let's start with data types. So here are the different types of data. The first type is numeric, and these are just numbers. They can be whole numbers or they can be decimals. The second type are character variables. These are words or categories. And when you input a character variable, it has to be in quotes for R to understand it. So the most common types of variables that you'll work with are probably numeric and character, but there's also a few others. Integer variables are whole numbers. They have to end with a capital L for R to read them as integers. If you don't put the L, R will just read it as a numeric variable. Logical variables basically are true and false, and they have to be in all caps. Complex variables deal with impossible numbers, and raw variables are basically byte storage. And keep in mind, raw and complex variables are pretty rare, so we're not going to cover them in an introductory course, but we thought we might mention them. Okay, and here are the different types of objects you can make within R. So the first one are atomic vectors. These are usually just called vectors, and these are the most basic type of object, and they consist of one line of one type of data. So a line of numeric values or a line of character values or whatever. The second type are lists. And these are made up of one line of multiple different data types. So vectors are one type of data. Lists contain different types of data. Then you have factors. Factors are made from vectors, and they store categories in a vector by level. So the example there is that if you made a vector with a bunch of different seasons in it, you can make a factor that contains one level for every season. Matrices are two-dimensional storage grids with one type of data, usually numeric data. So basically, it's like a two-dimensional vector. And vectors are one row and one column, while matrix can contain multiple rows and multiple columns. So these are not super common. A data frame is a two-dimensional storage grid with multiple types of data. So this is basically a two-dimensional list. And data frames are useful for storing tables and data sets, and these are very common. And the final type are arrays. Again, these are not very common, and they can store multiple dimensions with one type of data, usually numeric data. So it's similar to a matrix, but while a matrix can only have 2 dimensions, arrays can have 3 or more. And like matrices, these aren't super common. We're not really going to spend a lot of time in matrices or arrays in this course because they're not common. So here's just a chart to go over what I just talked about. On one dimension, you have the number of dimensions. And then on the other axis, you have different types of data. You see vectors, lists, matrices, data frames, and arrays. So we know what an object is. Now we're going to try to make them. So the operator you would use is a less than sign and a dash, which you can see looks like an arrow. So the setup would be the name of the object, less than dash, and then whatever type of information that you want to store. You can see some examples here. You can put a less than dash 10.5, and every time you type in a, R will read that as a 10.5. If you wanted to make a vector with multiple values, you would put in the name of the object, less than dash, and then you'd put a C with a parentheses and list out your values in the parentheses separated by comma. Since these are character values, we're putting them in quotes. You can see in the example with the vector Z. If you wanted to use make factors from this vector, you would put the name of the object, less than dash, and then the word factor with the name of the vector in parentheses. So in this case, you were making a factor out of the Z vector. And you'd also use the same syntax for matrices, arrays, and data frames. Okay, so you can do basic arithmetic with objects in R using the plus sign, minus sign, the asterisk for multiplication, and a / for division. If you want to use the results, you can use a print statement. So you'd write print, open parentheses, 2 + 2, and close parentheses. That's how you do a simple addition problem. You can do arithmetic using vectors. You can use data frames, matrices, and arrays as long as they have numbers in it. Basically, any numeric object you can do arithmetic in. And if objects are different lengths, you can still use arithmetic, but R will give you a warning. When it gets to the end of one object, R will just start again from the beginning until the longest object is finished. All right. And now we have our first coding exercise. So if you don't have FSU Virtual Lab open, please do that now. And I'll hand it off to Eli.
So with exercise 1, we had x = 20, y = 4. How would we add, subtract, multiply, and divide? So if I wanted to go up here and say, I'm going to say x is 4, and I have y is 20. So if I run this, it'll get stored in R in this top right-hand number 2 panel of like x is 4, y is 20. So let's say I want to have, let's say, addition, like it's a x plus y, and if I wanted to see what that was, hold on. Did that not print? Oh, right, because I'm doing it up here. So if you print up here. Oh, yeah, I need to run the whole thing. So it'll print out 24. You could also just do x plus y. And it'll still print, but it won't store it if you do it this way. As a side note, R is case sensitive. So if I run lowercase x and lowercase y, you're not going to have either. As you can see in the bottom here, object lowercase x is not found. So I'm going to go ahead and establish that. Likewise, if I wanted to say subtraction, and assign that as x, well, y minus x, and then proceed to print this object I named subtraction, and then run this, it'll do that. Similarly, multiplication, x times asterisk y. Oh wow, I wrote that wrong. I wrote multiplication. A feature I do like about RStudio is that it'll highlight at the bottom if you select something. Does that. And then lastly, division. Assign it with the left pointing arrow, x y divided by x. Let's say we did that. Pulling this up, run this, and we get 5. And then for the second exercise, oh, you have it over there? Oh, cool. All right, so let's say we have all this stuff. Okay, we have this problem, like a practical problem where we don't have a data set necessarily. Let's say we have S-bucks stores. And we know that there's 15,444 of these. And we know that there's 50 states, 5 territories in Washington, D.C., so that's 56. So if I wanted to make an object that just had that object as 56, and what you can do from here is like average stores. And what you can also do is you can divide and do arithmetic with the objects you make. So let's say I have S, the stores object I made up here for this number of stores. And then I divide that by states and territories object I made down there. And I execute this code up here with this top run function up here. Oh, I did not print. Don't forget to print. Average stores will be about 275. The results you get will pop up down here in this console at the bottom. And you can, it also serves as a history, so you can scroll up and down to see every single thing you executed. So it's just like I did the print average stores, it's down there, print for division is down here on the bottom third, multiplication, all of that. I will hand this back over to Semi real quick, if I can figure out how to get this mic off.
All right, so now we're going to talk about a function. So a function is when you give an R instruction on how to do something. So in the last exercise, we talked a lot about the print function, and you're giving R the instruction to print out the results. So that's a good example of how a function works. When you're doing a function, you would write out the name of the function, followed by parentheses with your data in the parentheses. So in the last exercise, we use arithmetic to calculate the mean. However, this isn't always efficient with large data sets. So you can use the mean function and put the name of the object in the parentheses. So you don't have to type in every single value one by one. You can also do this with median and quantiles, like the slide shows. All right, so I'll repeat that, the slide on functions, because I think a couple of people missed that. We're having some tech problems. Okay, so a function is when you give R instructions on how to do something. So we talked about the print function in the last exercise. We used the term print to get R to print the results for our arithmetic problem. And when you're doing a function, you write out the name of the function, followed by parentheses with your data in the parentheses. So in the last exercise, when we wanted to calculate an average, we just used arithmetic. But that isn't always efficient with large data sets where there's lots of different values. So one way to do that a lot quicker is using the mean function. You can also do this with median and quantiles. All right, so now let's talk about making data frames. There are 2 ways to do this. You can import data, which we'll talk about in a minute, or you can make them from scratch. And if you make them from scratch, you have to start by making a vector for each variable. And we talked about how to make a vectors before, but just to go over it again briefly, you put the name of the vector, in this case the variable name, you put less than dash, then you put C, open parentheses, list out your values with commas in between, and then close parentheses. Once you have all your vectors ready, you use the data frame function, which is data.frame, and list out all the vectors you want to combine in parentheses. And of course, you can save that data frame as an object so you can refer to it later and use it for different functions. If you want to look at your data frame, you can use the print function. And just to go over that again, you make a vector for each variable, then use data.frame function to combine those vectors into one data set. All right. If you're working with larger data sets, maybe it's not practical to do all that from scratch. That's a lot of different steps. So this is where importing data can be useful. And one way to do that is by using a read function. So you can put read.cvs or whatever file type you're using. If it's not a CVS, it might be Excel or something like that. And then put the file path in the parentheses in quotation marks. And now when you do this, you have to make sure you're using forward slashes and your file type is in quotes. So we have an example on the screen right there. So just in case you're not familiar with what I mean when I say file path, I'm sure many of you are, but here's an easy way to find it. Find the file on your computer and right-click it. Click on Properties if you're using a Windows computer, or Get Info if you're using a Mac. And you can find all the information about the file path. It should be listed in Location. Now, if all that just sounds too complicated for you, RStudio has some user-friendly ways to import data. There are multiple options actually within RStudio. So in panel 4 on the bottom right, you can look through the files on your computer and right-click, and there should be an option that says Import Dataset if you have the dataset saved onto your desktop already. In panel 2 in the top right section, there should also be a button that says Import Dataset that can help you out. So this is one of the advantages to using RStudio. You don't have to remember anything complicated. All right, so everybody makes mistakes, and that includes R. Sometimes when you're importing a dataset, it will categorize it into the wrong type. It'll categorize variables into the wrong type. So you may have a numeric variable that R for some reason is reading as a character variable, but this can be fixed. So the first thing you need to do is use the class function to figure out what type of data a certain variable is stored as. If you want to change the data type, create a new object, and you can use the as.numeric function to store it as a numeric variable. If you want to store it as an integer, you can use as.integer, and then so on. Once you have your imported data, you might want to make vectors out of your newly created data frame. So we talked earlier about how to make a bunch of vectors and combine them into one data frame. Now we're going to talk about how to take a data frame and break it up into smaller vectors. The way you do this is by creating an object with the same format we've been using. Object name, less than, dash, then put the name of the data frame with a $sign, no spaces, and the name of the variable that you want to turn into a vector. And you can even combine those vectors to make a new data set. So there's an example right there on the slide. My variable vector, less than, dash, my data frame, $sign, my variable. Here's the exercise we have for that. So I'm going to hand it off to Eli so we can introduce this next exercise.
All right. So with this exercise we're going to import, we're totally not endorsed by Starbucks, I swear, even though they are in FSU libraries. We have the Starbucks drink menu and nutrition data set available in the Google Drive that is in the chat. If that needs to be dropped in, let me know. We'll first import that data set, make some objects for calories, caffeine, and milk type, and also check what type of data it's stored as, and then converting as such to get the mean and median caloric content and caffeine content for the average Starbucks drink. I'm also going to have to go ahead and pull out so if I pull up properties for the version of this file I have, let's see, so the file path, so I'm going to say, let's say I want to make this SBooks, not stores, just regular SBooks. Okay, and I'm going to be read.csv. Unfortunately, I'm not going to be showcasing it here. We are using an FSU libraries computer here. With the read.csv function, you'll also want to make sure it's in quotation marks. So first, it's like your file path starts with your the location of the file. In Windows, oftentimes the reason that we emphasize making sure that the forward slashes are a thing, because in the file path on Windows, it will get written, it'll make it backward facing instead. Oftentimes, I have had many situations where it's just like, oh, no. It won't go, but it's only because it's not forward slashing, it's backward slash. So now we can, another fun, nice little feature about RStudio is that once you have your data up here, you can click on it to see what's going on up here. So we have this whole entire data set of the Starbucks menu, courtesy of Kaggle.com. We have every single variable up the top, beverage category, beverage. Ooh, that is looking crunchy on here. So if I wanted to make, let's say I want to make a calories object, right? Well, I'm going to write this down at the bottom because I might want to go through here and make sure that what data is up here, because the name of the data of each variable is important. So I want to make calories, SBooks, $sign to call that it is indeed coming from calories. Oh, actually, I could do it up there. I could do it in the third panel. This is just a personal workflow thing I tend to do. Okay, so we have caffeine. Left arrow, dash, SBucks to call the data set I have. $sign. Let's see, where's the $sign? And then we have, I personally do not enjoy typing out everything, but because sometimes these get very long depending on who. So we have caffeine. And then finally, I believe it was milk type, right. So we have milk type, the less than sign and dash to be like, here, point towards this thing. SBucks, which is what I named this data set I imported. $sign. I'm going to go with milk type numeric because this data set has both a character and a numeric type. And if you want to check, we have at the bottom here, class, let's see, calories. Why am I having a hard time spelling? So class for calories is integer, makes sense. It is a number. Caffeine. This is a character variable for some reason. The reason I wanted to show the code down here in this bottom console, because if you have any character data at all, there's actually a few drinks in this data set where it says varies, and that won't register as a number. So this is why. So if I want to convert this into a number as numeric, caffeine, so that there's also this is a little bit of a warning sign, but the NAs basically mean that will exist as non-existent data. All those varies become NAs. And just to be on the safe side, we'll check the class of the milk type too. I put that in uppercase. Integer. I imported the integer version of that particular variable because there's the character type and then also the numeric version. And we wanted to find the mean for, let's say, caffeine. Is that not gonna? We have NAs in here, so there's a way around this. So na.omit. I believe it was na.omit caffeine. Oh wow, I did not spell that correctly. Okay. So if you have NAs in your how did I do this again? Oh, right. Sorry about that. So if I want to actually get that, excuse me, there's a function called na.omit that will take out your non-existent, your NA variables, not your variables, your data set points. I'm going to call this only numeric caffeine and assign it as an object, so na.omit caffeine. So this will take out all of the NAs, so then we can take a mean statement. What? What am I doing wrong here? I am so sorry, y'all. What am I doing wrong? I'm doing something way wrong here.
Did you change it to a numeric?
I thought I did. Did I not? Wow, this is very... as numeric caffeine. I'm going to do it this way. More caffeine as numeric. Just to make extra sure. I'm going to go NA caffeine, NA.omit to make sure that all of those NAs are gone. And finally, we should be able to get the mean. There we go. My apologies. Sometimes you have to remember how to do things. So essentially the NA.omit, it won't calculate a mean if you have an NA in your data, as in up here. Thankfully, we already have the object now for NA caffeine. So now we can get that. Likewise, we can get mean calories, median calories. Sometimes you have to do a little bit of data cleaning here in order to make sure that it can calculate a thing. But just as a warning though, you will want to make sure that you account for the number of data points you have once you have all those NAs gone. I think that was the end of that exercise.
All right, so now we're going to get into some data analysis. So we're going to start with ANOVAs. Here's, just in case you've been at a stats class for a while, here's a quick primer on ANOVAs with the Oxford Dictionary definition that you can read. And then go to the next slide. So a simpler way to understand that is that ANOVA, we're just comparing the mean and spread of a quantitative variable between two or more categories. Okay, so for example, this chart compares the average lifespan between dogs and cats. All right. So to do a one-way ANOVA, like the example we just showed you about the dogs and the cats, you need an independent variable. This would be your categorical variable, so a character variable, and a dependent variable, which would be your numeric variable. To run the ANOVA function, you would put AOV, and then in the parentheses, you would put the y variable, a squiggly line, and then the x variable. And of course, you can save this as an object. So if you want to view the results, you would use the summary function. And as a side note, if you wanted to run a two-way ANOVA, you would list two x values with a plus sign in between them, just like the example we have at the bottom. Just keep in mind, you want the y variable to go first. Okay, so this is how we did the cats and dogs examples from earlier. You can see the first two lines of code are just making an object for each variable we want to use. Then the third line involves using the ANOVA function with our two variables and saving it as an object. The y variable is the lifespan, so that's listed first. And then the last line is using the summary function to look at the results. So when you use a summary function, this is what the results look like in R. All right, so now we're going to use a built-in data set to do this exercise. R has some built-in data sets, so you don't even have to download them. So you don't need to import anything if you want to follow along, and I'll hand it off to Eli.
All right. I'm going to try to make sure that y'all can see this up at the top in this first panel. But I will, however, show you print tooth growth, which is a default R data set. So you don't even have to import this one, which is pretty cool. It'll print down here in this third panel. R has quite a few little default data sets that they're just really good for experimenting with and like testing things out with. I highly recommend it. Just for the background of this data set, it was basically testing guinea pig growth of teeth based off of whether they had a vitamin C tablet or orange juice. So from here, if we want to be like, here's the length of a tooth growth. Length is like, however, I will point out, even though we still have a default data set, it still has it still has to be run. It still has to be called with a $sign, and then I think I called it supplement. So tooth growth, $sign, sup. Thankfully, it pops down here. So if I want to make this object up here for this particular ANOVA, I go do the assignment arrows, AOV, I believe, did I do length? Like, because the length is the dependent variable in this case, tilde, and then sup. And we can run this. It does get length not found. Oh, right. R is, once again, case sensitive. Okay, and then I can do summary of tooth ANOVA. And if I highlight this and click the run button up here, it'll give me everybody's favorite with p-values, degrees of freedom, the whole shebang. In R, as a side note, significance codes are down here at the bottom. We have a little, it's very subtle. There's a little period down here to note that this is about significant at like a 0.1 confidence level. It's kind of tiny, but it is there. It will tell you if it's significant or not. If not, if you feel comfortable with reading statistical output, you can infer it that way as well with F values, all that jazz. Rock on.
All right, so now we're going to talk about regression. So once again, if you need a quick primer of what a regression is, we have the definition right there. You can go to the next slide. But if you want that in layman's term, we're just looking at the relationship between two quantitative variables. So the chart on the screen shows the relationship between the amount of time a student studies and their GPA. That's a very simple linear regression. So in order to do a linear regression, you need two variables, and they both need to be numeric. To perform a regression function, you would type in LM, and then in parentheses, you type the Y variable, a squiggly line, and then an X variable. Very similar format to an ANOVA. And of course, you can save this as an object and use a summary function to view it just like we did with the ANOVA. And if you wanted to do a multiple regression, you can list out your X values with a plus in between them. So once again, it's a very similar format to the ANOVA. So going back to the example we talked about earlier, if you wanted to look at the relationship between the time a student studies and their GPA, first you import your data, then you make your variables, then you perform your regression function with the LM. Since GPAs are a dependent variable, that goes first. Then you use the summary function, and the results look like this. All right, so once again, we're going to use a built-in data set, this time on tree growth, and I will hand it back to Eli.
All right. We will print out the trees. I wish we could print trees in real life, but unfortunately that's not a thing. But we will print the tree data set, which is useful for here. If I can go ahead and actually press the run button. So down here, if I highlighted trees, this is the built-in tree data set. It'll give you the three variables of girth, height, and volume. From here, what we can do, I think we were going to do girth and height. Okay, so let's say, I'm going to name this girth 2 because I feel like naming it that. As long as you have, so we have our trees data set first, followed by the original girth, followed by length 2. As a side note, length is also a function in R. So in this situation, length, height. I don't know why I was thinking of that.
The last example.
Yeah, okay. Tree regression. And then I will assign that to be linear model. I like to remember the linear model function or for linear regression as LM. So we have, was it supposed to be dependent on, I keep forgetting.
Predicting height.
Yeah, yes, okay. So length 2, tilde, girth 2. And then we'll want a summary of tree regression. I like how it memorized what I type because I'm never very good at remembering my object names. Did I run that? Oh no. Did I just delete all of my code? No, I didn't. There we go. It came back. Yeah, Control Z. So I ran all of that, and it pulled up. Here's the formula we have. With linear regression, you get an intercept and you get the p-values, estimate, standard error, all of that. All of the stuff one would hope to find in a statistical. Why is this screen so crunchy? Now I can't even read my own summary statement. This is... The significance code popped up. There is indeed a difference between the width of a tree and the height of a tree. So it's like up to 0.01 confidence, which is pretty nice. It'll give me like the R square at the bottom here, F statistic, residual standard error. Fun stuff. What questions do y'all have? Any questions? Feel free to ask at any point, by the way. Would you like to move on? Okay. Okay. Oh, actually, hold on. Can you go over the intercept? What would that mean? Okay. So the intercept of the line, I might want to actually like explain. So like the idea. Wait, what?
I don't know if people on Zoom can see anything you're writing down.
Would y'all be able to? Does any like on Zoom? Would y'all be able to see like the blackboard back here? Or the whiteboard, I should say. Why did I say blackboard? It's a whiteboard. Okay. Okay, I have an idea of what I might be able to do. So I might be able to stop share and actually show this in the PowerPoint slide instead. So the intercept would be this point here where it like basically cuts off at 0, like your y and your x intercept. Essentially, like if everybody, do y'all remember y equals mx plus b? That is what the intercept is in this case. So in this example here, like where it has 0 for time studied, this would be like where the y-intercept hits, and it's like down here. And so in R, so what this intercept here is like if you had a formula of y equals mx plus b, or rather like y equals your intercept variable and then your regression, your independent regression variable. So you'd have like your predicted value of your intercept here is your estimate of like, so you'd have like y, your estimated y is like 62 point this plus this estimate for girth times however wide your tree was. So you can use this in a practical.
If your x is 0, it's your predicted y.
Yeah, if your x is 0. Yeah. Hold on. Okay, cool. Okay, so that turned out to be a pretty good explanation. All right. What other questions do y'all have? Are y'all comfortable moving on to the next part of the PowerPoint? Okay.
Now we're talking about making graphs within R. And we do that using the plot function. And this time the x variable goes first. So let's go back to the data on tooth growth and plot supplement and length. So if you try it out, you should get something like this. Again, the plot function in parentheses, supplement, comma, length. And you should get the box and whisker plot that you see below. And the next example. So now let's do the same thing with the trees data. So we'll plot girth and length. And if you notice, whether you try it yourself or just look at the graph that's on the PowerPoint, something is different. The previous data set created a box plot, and this one is a scatter plot. And when you use the plot function, R will automatically choose the type of plot that it thinks is best for the specific type of data that you have, which can be very helpful if you don't know how to present your data, or it can be annoying if you have a specific format in mind. So if you wanted to add a regression line to this scatter plot, you would just use the plot function and then add a plus, and then use the function AB line, then run the linear regression within that. Now, if you save the linear regression as an object, you can just put the name of the object instead of writing everything out again. So you just put AB line and then the name of the object in parentheses, which is especially useful for longer codes. This one's a relatively short code, so on the example on the slide, I just typed everything out again. All right, now let's talk about packages. So a package is basically a bundle of functions that you can download into R. There are over 10,000 packages that can be downloaded. They give you a bunch of different features that don't come with the default R. And in order to install a package, you can use the function install.packages and put the name of the package in parentheses within quotes. To open the package, you need to use the library function and put the name of the package again. So you only need to download a package one time, and it'll automatically be downloaded forever, but you will need to open it using the library function every time you open R. So if you want a list of packages available for download, GitHub has a good list. It's called Awesome R. And just as an aside, a lot of packages are available within R, but some of them have to be downloaded onto your computer first from another source. But we're not going over that today. Today we're just going to talk about packages that are available within R. So I will let Eli talk about that.
I feel like a nice introduction that my personal favorite is install, like there's a beeper function. All it does is make a beep. So I personally find it to be a very friendly way to see if it got installed. Install packages beeper. All right. The console will let you know if it's getting installed. It's chugging along. It's doing its computer thing, installing. All right, and so beeper. I think it's beep. It probably won't do it because I think this laptop is muted. But if you were to run this, is that beeper? Or I thought it was just beep.
You got to use the library function.
Oh, right. I feel like I gotta pay attention to her. Okay. Library. Beeper. Okay. Beeper. Beep. Sound equals 1. Hopefully this will run. Maybe it'll make a sound on our end. Maybe it won't.
The computer's muted.
It also said it couldn't find the function beeper. I think it is just beep. If you have it on your end, it should make a beep sound. If not, something's not working. Yep, there we go. So, hello. It works if you only use beep. Yeah, I don't use beeper that often. Beep 1 or sound equals 1. There's like 10 of them. I feel like this is just a very nice way to show how to install a package. But I think the more important one that we're gonna do is install packages. Hey, I heard it over there, nice. ggplot2. This one, we're actually going to get a little bit more use out of a little bit later. So once again, in the console down here at the bottom, it's chugging along, being like, we're trying to install this package. All right, I'll hand this over to Simi because we're going to be talking about what we do with ggplot2.
All right, so today we'll be installing and using the ggplot2 package. And just as a reminder, even if you already have this installed, every time you open R, you have to use the library function to reopen the package every single time. And the ggplot2 package is one of the most common packages used within R. A lot of R users prefer using this to make graphs rather than the plot function because it just has more functions and customizations. We'll talk about some of them today. All right, to start, any ggplot graph has to start with ggplot open parentheses, the name of the data set, and then the letters AES, and then the X and Y variables in another set of parentheses separated by a comma, and then you can use the plus sign to add more features. It looks very complicated. It's really not. We'll go over it slowly. Okay, so let's go back to our tooth growth data that we've been working with. You start with the term ggplot, and then in parentheses, you would put the name of the data frame. In this case, it's tooth growth. Then you would put a comma, AES, and then another set of parentheses, and you would put the X, so in this case, that's sup, and then the Y, which in this case is len, for length. And from here, you would add a box plot, which would be plus geom underscore box plot. So the whole line of code would look like this. And if you do all that, you should get a box plot using ggplot. All right, so now let's do the same thing with trees data. Use the same baseline, you just swap out the name of the data frame and the X and Y variables. For here, you would use a scatter plot using geom underscore plot instead of geom underscore box plot. And then you would add a regression line using geom underscore smooth. And in parentheses, you would put method equals lm. And you'd put the lm in quotes, by the way. So ggplot can be kind of long and clunky, but it has a lot of features and it's really useful. Honestly, we could do an entire course on just ggplot. This is only just scratching the surface, but this is a good introduction. All right, so let's talk about a few other things you can add to your graph. So labeling is obviously very important. You can add plus labs, LABS. And within parentheses, you can add labels for the x and y axis. You can see x equals and then put the label in quotes, comma, y equals with the label in quotes. That's a way you can label certain axes. Make sure they're separated by a comma and make sure the names of the label are in quotes. A lot of errors in R, just so you know, just come down to forgetting a comma or forgetting quotes. So always make sure you double check that type of stuff. You can add details in the parentheses of the box plot or scatter plot. For example, you can change the colors of certain things. These are some of the customizations that are available in ggplot that aren't available in the regular standard plot function. And of course, you can export your graphs and save them in panel 4 on the bottom right. Okay, so now we're going to take everything we learned today and put it all together, going back to the Starbucks dataset that you imported earlier in this lesson. And I will let Eli introduce this exercise and talk about how to put everything together.
So thankfully, we installed ggplot2. And also, as an extra fun side note, we've already gotten some regression stuff going on for, well, not our regression, but we have vectors already established up here. Well, no, I wrote those down here. Oh, wow, that's a long history. Well, I did have the calories. Okay, let's see. Where did I... This is why it's a good idea to do it up here in 1 instead of down here in this first panel as opposed to this third panel, just because this is a very clunky. Yeah, yeah, the environment. Yeah, this is true. This is true. This is very true. Okay, so I'm going to do it this way. We do have the caffeine stored up here and calories somewhere. Yep, calories and caffeine. So let's say I want to see, is there a correlation between calories and caffeine? So I'm going to do caffeine.
Make sure you're using the numeric version of caffeine.
Good point. Caffeine regression. And then assign this as an object. I'm going to do lm. I'm going to double check and make sure. Did I make calories? I did it lowercase this time. Calories to NA caffeine. This is the purely numeric version of caffeine. Caffeine regression. Go ahead and run this. Oh, yeah, that's not going to run nicely. So, thankfully, though, I have more caffeine so that the observations for calories matches up with the observations for caffeine in this instance. I don't know why it says A down there. But we can, so we'll do a summary of caffeine regression first to see what's happening. And then we'll go ahead and visually show what's going on with our fun friend, ggplot2. So we'll do ggplot, actually, caffeine reg plot. I think you do it this way. No, I don't. ggplot, we're gonna have S books in all caps. It should be, for the linear regression, we're gonna have more caffeine compared to the calories in this first set of nested stuff going on here, plus geome point. Geome point, I don't have anything in that. And then, like, no, I don't, yes. Geome smooth. All right, and I believe that should run. That should run. Run, please. Oh, what did I do wrong here? Did I forget? What did I do wrong here? Okay, so it should be AS. Oh, I know what I did wrong here. Hold on. I didn't have a closed parentheses. That's what I did wrong here. as Simi said, you gotta have your closed parentheses, because there we go. So, in the fourth column, well, fourth panel over here, we have our results. Now we can visually see if caffeine has a correlation with calories, and the answer is no. You can have nothing. You can have no caffeine and a bunch of different calories. You can have a lot of caffeine and all sorts of different calories. There's some things down here that have hardly any calories, but there's a lot of caffeine in it. So basically, caffeine doesn't mean anything in terms of calories, which makes sense as we saw up here. We don't have any statistical significance for caffeine and calorie content. Likewise, we can do a ggplot with ANOVA here with SBucks once again. And this time, I believe we're comparing, right, milk type, because milk type is our dependent variable in this case. And then we were going to compare calories. It's like, do we have, okay, that's lowercase, plus geom box plot. I'm going to do color equals green, because green is cool. It should work. If not, I must have done something terribly wrong. Okay. Okay, I did something wrong here. Let's see. Oh, I know what I did wrong. Okay. Okay. That's not right. Okay. I know I could, no, okay. Yep. Let's see. Did I add in the wrong milk type? Oh, I did it as an integer, that's why. Hold on. Okay. I should have, okay. Well, that would normally be how to do ANOVA. Let me go ahead and try this differently. I apologize for the inconvenience here. Oh, you know what it probably is? It's probably because I did it as a integer, not a numeric. I'm just going to go ahead and use the... I'm going to go ahead and just run this as standard. I apologize. I know for a fact I coded this in advance in a better method. The thing about saving scripts in R is that you can save things in advance. I know for a fact I saved this better. Yeah, this is what I should have. Let's see. Okay. What did I do wrong here? Live coding can be difficult sometimes. I apologize, y'all. Let's see. What did I do wrong here? I'm going to try this again because I know this should work. Geom box plot. Okay. Okay. My statement was mostly right. Something's wrong with the fill statement here. I don't know why that's not working the way it's supposed to, off the top of my head. This is generally how a ggplot ANOVA state graph works. Yeah. It does save in your bottom fourth panel over here on the right hand, bottom right hand, save image as directory. If I wanted to save it as a PNG, pictures. Sure, I guess I'll save it here. Oh wait, no, the directory. So you have to send it to a certain area on your computer. Save it as a specific format type. And it will save this out as a PNG. I had it saved as a PNG. So you can export this out. You can also specify the type, the exact size up at the top. You can also save it as a PDF. I'm going to go ahead and stop share and send it back over to Semi.
All right, so as we just said, you can save, if you want to save your code, you can do so in panel 1. If you want to come back to it to work on it later. If you wanted to, you can save everything we did today, so you can reference it at a later date. If you want to leave a comment or note for yourself, you can do so using the number sign. Anything you write after a number sign will not affect how your code runs. It's just a way to make notes throughout your code. And just a reminder, if you want to use ggplot or any other package, you need to open it with the library command every single time you use it. So library, parentheses, and then the package name. So that would be ggplot2. You never need to download it again if you downloaded it once, but you need to open it with the library code every single time. All right, so here are some more resources if you want to learn more about R and specifically ggplot. You can go to Stack Overflow, and they have a forum entirely dedicated to ggplot functions. Once again, we could teach an entire class on that. There's so many different things you can do. We just barely scratched the surface. There's an R graphics cookbook that you can check out from the FSU library that talks about the different functions that R has. GitHub has a list of packages that you can look through if you want to look at other packages besides ggplot. And there's an entire search engine called RSeek that you can use to find answers to your questions. And of course, you can always, always, always request assistance from your librarians. You can submit a ticket, and we'll be happy to help you with any projects. All right, so here is the Q&A. All good things must come to an end. So this is the end of our slideshow and the beginning of our Q&A. If you have any questions, feel free to type it in the Zoom chat or raise your hand. If you want me to go back to a certain slide, or you want Eli to open up RStudio to demonstrate something, we'd both be happy to do that. But thank you so much for attending, and it was nice to have you.